Hello everyone! Welcome to our lecture series on the Finite Element Method, or FEM. Let's begin with a simple question. Why do we need the Finite Element Method? Many engineering structures are too complex to solve using exact mathematical equations. That's where FEM comes in. It helps engineers analyze and design complex structures accurately and efficiently. As shown in this poster, FEM is widely used in civil, mechanical, aerospace, and thermal engineering. Although the applications are different, they all use the same numerical approach. That's why we say, one method, infinite applications. In this chapter, we'll learn the basic concept, history, applications, and complete workflow of the finite element method. Now let's understand the basic idea behind FEM. The principle is very simple. Instead of solving one large and complicated problem, we divide it into many small and manageable pieces. This process is called discretization or meshing. Look at the bridge shown in the poster. First, we have the complete structure. Then it is divided into many small finite elements connected at points called nodes. Each element is easy to analyze mathematically. The computer solves every element individually and then combines all the results to predict the behavior of the entire structure. Remember one important point. FEM provides an approximate solution. However, as we increase the number of elements, the solution becomes more accurate. This improvement is known as convergence, which we'll study in detail later. Let's take a quick look at the history of FEM. The development began in 1851, when Shellbach introduced ideas related to triangular discretization. In 1943, Richard Courant applied triangular elements to engineering problems. A major breakthrough came in 1956, when Turner, Clough, Martin, and Topp published the stiffness matrix method for structural analysis. Finally, in 1960, Ray Clough introduced the name Finite Element Method. Today, FEM is combined with artificial intelligence, digital twins, and high-performance computing to solve extremely large engineering problems. Now, let's understand why FEM is so accurate. Imagine trying to draw a circle using straight lines. If you use only 3 sides, you get a triangle. With 6 sides, it looks more like a circle. With 12 sides, it becomes even closer. And if you continue increasing the number of sides, the shape almost becomes a perfect circle. FEM works in exactly the same way. Each finite element provides only an approximation. But when thousands of small elements work together, the overall solution becomes very close to the exact solution. This process is called solution convergence. However, increasing the number of elements also increases the computational time. Therefore, engineers always try to find the right balance between accuracy and computation. Now, let's see where FEM is used. In civil engineering, it helps analyze bridges, buildings, dams, and tunnels. In aerospace engineering, it predicts stresses in aircraft structures. Automotive engineers use FEM for crash analysis and vehicle optimization. Mechanical engineers analyze gears, shafts, and machine components. FEM is also widely used for thermal analysis, vibration studies, fluid flow, and even electromagnetic field analysis. Because of these applications, engineers can improve designs, reduce the number of physical prototypes, lower costs, and develop safer products. Every FEM software follows almost the same sequence of steps. First, we define the engineering problem. Next, we create the geometry of the model. Then we generate the mesh by dividing the geometry into finite elements. After that, we assign the material properties. The next step is applying loads and boundary conditions. Finally, the software solves the equations and provides results such as displacement, stress, strain, and reactions. But remember, obtaining colorful contour plots is not enough. A good engineer always checks whether the results are logical and physically meaningful. That's why engineering judgment is just as important as the software itself. If you found this lecture helpful, please like the video, subscribe to the channel, and share it with your friends. Thank you for watching.